Okay, I'm having a look at our Term 3 Week 6 quiz for Year 9. So the first question I've got here is a proving similar triangles question. So I want to go through those steps that we need to go through to prove that we have similar triangles. Now, when we look at our diagram, we don't have any numbers for lengths of sides there. So we know it's got to all be about the angles. So to start with, I'm going to look at these two angles here. So I know that they're equal because that of opposite angles are equal. So I can be writing their angle, and because I want to differentiate between the top one and the bottom one, I'm going to say ABE. So angle ABE is equal to angle CBD. And my reason for that is that opposite angles are equal, and that's that little coded reason for that. Then we have, and I'm going to use my highlighter to show, we have these parallel lines, which means we can use the Z rule. So I've got this one here, that Z rule. So that's going to tell me that the angles that are here, I'll use across, and here are going to be equal because they are alternate angles. So I can then say that angle AEB is equal to angle DCB, and that's because of the Z rule, that alternate angles are equal. I could then use the knowledge that if I've found two angles in two triangles that have a matching one in each, that the third will also be equal, because when we add our angles in a triangle, they add to 180. So if we already know two of them, we can work out the third. And if we know those two are the same in each triangle, we can, it implies that the third will also be true, will also be equal. The other way we can see that in this triangle is to use the Z the other way, and we can say that angle EAB is equal to angle BDC because of the Z rule. We now have three statements. We always need to have three for a triangle to make sure we can prove similarity. We now have those three statements, and my coded reason for that is going to be AAA, so angle, angle, angle. The other ones that I could have had were side, angle, side, but we don't know the scale factor between the sides because we don't have any side lengths, so we can't use that. We could also have had three sets of sides given to us, on each, like three sides on each triangle with the numbers, and it would have been able to prove the scale factor on those, but we don't have any sides, so we can't have that. The other coded reason that we have is RHS. That's for a right angle triangle. We haven't got any notation here or anything to tell us that those are right angle triangles there, so that one's out of the options as well. I then want to finish by writing the similarity statement that, and this is where I need to be careful and label the same way around. So if I go A, E, B, I want to start on that one where the yellow is, have the cross in the middle, and finish it. So I've got D, C, B. So we're just being careful with the order that we name that in. Then for number 2, we've got some triangles. Now I put these together to see if students would be able to work out which ones were our trig ratios and which ones were Pythagoras theorem. So looking at those 4 triangles there, the way that I know which method I'm going to use is I'm looking if I have any angles given to me or asked for. So in these ones, there's an angle shown or wanting to find out. Here I don't have any other than the right angle, and I'm looking at something about the 3 sides. That means I'm going to be using Pythagoras theorem. So I'm going to write my rule up there, c squared equals a squared plus b squared. I'm then going to need to label my triangle so I know what A, B, and C are. So my C is the most important. It has to be the one opposite the right angle. And then A and B can go wherever you want to put them. So I'm going to put A here and B there. That means I can then write 19 squared is equal to 11 squared plus b, and I can write b squared, or I can straight away change that to the x squared that's on the diagram. So then I need to do, over this side, 19 squared take 11 squared to leave me with the x squared. So I'm going to grab my calculator. I can do that straight in there and do the 19 squared take 11 squared. That gives me 240. And then I'm going to do the square root of that answer. and that gives me 15.49, and that will be what x is equal to. I also need to make sure I've put my units, so I'm going to put that, squeeze a little m in there for meters. For part B, I've got that angle, so I know I'm using my trig ratios this time. So I'm going to label my triangle first so that I know which ratio I'm going to use. I've got my angle here, which means the 11 is my adjacent. My hypotenuse is over here, which means my opposite is there with the x. That means I've got something with the O, something with the A, which means I'm going to use the tan ratio. So then I'm going to fill in what I know. So I've got tan of 50 is equal to x over 11. The 11 is on the bottom, so that means I can bring that over to the other side. 11 tan 50 equals x. And then I can grab my calculator and work that one out. 11 tan 50, and I get 13.109, so I'll change that to 13.11. And that's what x is equal to, and checking for units, centimeters. For part C, I'm going to go through that same process. So label, ratio, work out my answer. Labeling this one, I've got my A, O, H. So I have got a number or a letter with our A and our H. So that means I'm going to use cos theta equals adjacent over hypotenuse. I've got cos of 70 is going to equal 5 over x. My x is on the bottom, which means I can make these two swap sides. X is equal to 5 on cos 70. I'll grab my calculator and do my 5 divided by cos 70, and I get 14.619, so I'll round that to 14.62, and that will be meters for my units. For part D, I've got the same thing again. I'm going to label my triangle, A, O, H. This time I've got something with O and H. So it's going to be sine theta equals opposite over hypotenuse. So sine x is equal to 8 over 12. Now we want to find out what x is, so we need to do sine to the negative 1 of 8 over 12. So I grab my calculator. To do that, I'm doing second sine, 8 over 12. Press my enter, and I get 41.81 degrees. Okay, turning to the next page. We have some volume questions to start with. Now, in the first one, we're given the area of that circle there. So we're just using our volume equals area of base times height. So we're going to do 15 times 4, which is going to give us 60 meters squared. Oh, not 60 meters squared because we're in volume. So it's going to be 60 meters cubed. For the part B, there's a little bit more to do. So we've got our triangle base here, but we don't know the area of that. So we need to do our area of base times height. Our area of a triangle is a half of base times height. So we've got a half times 6 times 5, and we're multiplying that by the height of the entire shape, which is 8. So we've got 6 times 5 is 30, a half of 30 is 15, 15 times 8 gives us 120, and that will be centimeters cubed. Then we've got a surface area question. So we need to do our surface area of a cylinder is 2 pi r squared plus 2 pi rh. So then we've got 2 times pi times, and I need to be careful here because that's my diameter, so my radius is equal to 1. So I've got 1 squared plus 2 times pi times 1 times 3. So I'll grab my calculator. I'm going to have 2 times pi, 2 times pi times 1 squared, or I could have just left that little bit out because we know that's 1, and get 6.283, and we're adding to that 2 times pi times 1 times 3, and we get 18.85. We're going to add those two together, and I'm just going to go up and bring down that number there so that I don't have to retype it in, and I get 25.13, and that will be centimeters squared. Notice that I wrote the 85 when I wrote that there, but I kept all those decimals on my calculator. Now number 5 and number 6 are star questions, which means they're going to be a little bit more problem solving type or worded questions. So we've got find the area of the largest circle that can fit inside a square that has an area of 16 centimeters squared. So to draw a little picture of that, we've got a square. We're fitting a circle as big as we can inside that. Now we've been told the area of the square is 16 centimeters squared. We also know that the area of a square is side times side, or side squared. So if we do the square root of 16, that'll tell us what the side length was. So our side would be 4. So now we know that the side of this square is 4 centimeters. When we look at that picture, we know that then the diameter of that circle must also be 4 centimeters there. So that means we can work out the area of that circle because it's going to be pi r squared. If the diameter is 4, the radius is going to be 2. So then I'm going to grab my calculator and I'm going to do pi times 2 squared, and I get 12.56. And that is 566, so I'll round that to 57. And that will be centimeters squared. The last one here we've got is find the length of the ladder needed to reach the top of a building 5 meters tall if it needs to be placed 3 meters from the base of the building. So drawing a little picture, here's our building, it's 5 meters. We need to put our ladder out 3 meters from the base. So here's our ladder here, and we're trying to find out what the length of that ladder is. So we've got a right angle triangle there where you're going to use Pythagoras theorem, where we're finding that x value there for the length of the ladder. So we're going to write a squared plus b squared equals c squared, or the other way around, c squared equals a squared plus b squared. And my a and b I'm going to have as my 3 and 5. My x is the c. So I've got 3 squared plus 5 squared. I'll grab my calculator and I get 34 there is equal to x squared. So my x is going to be the square root of 34. So my x will be 5.83. So we will say, therefore, the ladder needs to be at least 5.83 meters long to be able to reach to that top of that building.